talk in the EC research seminar. We are happy to have Ishan Levy, who's going to tell us about the stable homology of Hurwitz spaces and Cohen-Lenstra moments for function fields.
Thanks. Yeah, I'm happy to be speaking here. Thanks for inviting me. So yeah, I want to talk about the Cohen-Lenstra moments for function fields and stable homology of Hurwitz spaces, and this is joint with Aaron Landesman. So first I'll tell you about, so the main thing I really want to talk about is the stable homology of Hurwitz spaces. But one of the reasons that's a really interesting question is because it's very closely related to the Cohen-Lenstra heuristics in arithmetic statistics. So I want to first start by telling you a little bit about that. So Cohen and Lenstra in around 1984, they made predictions about the distribution of class groups of imaginary quadratic extensions, imaginary quadratic number fields. So, and roughly what the predictions say is that the odd part of a class group should behave like a random abelian group, a random finite abelian group. And so here's sort of a precise version of that statement. So you can fix an odd prime p, and then there's a unique distribution, a unique probability distribution on finite abelian p groups. Let's call it mu, such that the probability of getting a specific finite abelian p group H is inversely proportional to the size of the automorphism group of H. So there's a unique distribution like this, the Cohen-Lenstra distribution. And what they showed, or what they predicted, is that this distribution describes the p part of class groups of imaginary quadratic fields. So namely, if you take that this number is the limit as the discriminant approaches infinity of the probability that if you take a quadratic number field, this is imaginary quadratic, and its discriminant is less than or equal to d, then the probability that the class group is isomorphic to H. So so they predicted that this distribution on class groups of imaginary quadratic fields, it limits to this distribution that's sort of like the random distribution. But so this has really been one of the main driving conjectures in the field of arithmetic statistics, but very little is actually known. And so, for example, what is known in the case that H, well, so to describe what is known, I need to first tell you what a moment is, which is this other word in my title. So this problem you can view as being as breaking up into an infinite sequence of problems. So that's because this probability distribution mu is determined by its moments, and its moments are associated to every abelian group H, every odd order abelian group H. And so the moment for an abelian group for H, what that is it's the expected number of surjections from the class group to H. So in particular, if you wanted to prove that this is the distribution on class groups, all you need to prove is that for every H, you can compute the limit. You can compute sort of the limit. So maybe I should first define the H moments. So the moments of this distribution are exactly they're the sum over all these abelian groups of the probability of getting a specific group times the number of surjections from uh, uh, from G to H. So if you can compute all of these numbers, that sort of determines this probability distribution. And so in particular, what you actually need to compute is just the limit of the expected number of surjections to any fixed abelian group. And if you can compute that for every abelian group, then you've sort of proven this conjecture. And so the only thing that's really known is that this the moment is computed for in the case of Z mod 3Z. So this is a theorem of Davenport and Heilbronn from 1971. And beyond that, for the original Cohen-Lenstra heuristics, nothing is known. There's a version of this at the prime 2 where progress has been made by Alex Smith recently. But I want to talk about a version of the Cohen-Lenstra heuristics over function fields. So this is about number fields. And so the analog of a quadratic extension over function fields is a hyperelliptic curve, which is a degree 2 extension of P1 instead of Q. And for function fields, the situation is much better. So let me describe what's known or what was known before. So first,
can I just ask, you said that there was a computation for Z mod 3. You said it was a computation of how many groups or the groups that surject to Z mod 3, but you did mean the class groups that surject to Z mod 3, or?
Yeah, so what they computed was the average number of surjections from a random imaginary quadratic extension onto Z mod 3. That's
from the ideal class proof of such an extension, not from arbitrary groups. Okay, thanks.
Yeah.
That makes sense. Thanks.
Mm-hmm. So let me first define this version of the moduli of hyperelliptic curves. So what this is it's going to be the set of monic hyperelliptic curves of the form. So they're going to be given by y squared equals some polynomial, and f should be over fq, and it should be square free and degree n. So and so in the case, so now you can ask the analogous question for function fields, namely if you choose a random hyperelliptic curve, does its class group look random? And so Ellenberg, Venkatesh, and Westerland, they proved a version of this if you sort of let the size of the finite field approach infinity, if you take a limit as q goes to infinity. So what they showed specifically is that if you take the limit as q approaches infinity, and let's say you also assume that q and q minus 1 are relatively prime to the order of the odd order abelian group H, then they showed that, and then you also want to assume that this n is odd, because that corresponds to the imaginary quadratic case. The even would correspond to the real quadratic case. And so if you take this limit as both q and n approach infinity of the expected number of surjections from the class group of this hyperelliptic curve to H, then what they showed is that this is 1, which is what you would get for this Cohen-Lenstra distribution. So they proved a version of this Cohen-Lenstra heuristics over function fields if you take a limit as q approaches infinity. And in 2012, they claimed they posted a preprint that claimed to do it for q sufficiently large compared to H. So not as a limit as q goes infinity, but just for all large enough q. But there is a serious error in their preprint that was pointed out by Oscar Randall Williams, And the thing I want to talk about today can be viewed as fixing this error. And so the result that we can prove is that, let's say, here's a version of the result we can prove. So if you take H, an odd order abelian group, then, and let's assume that the GCD of H with Q times Q minus 1 is 1. So like this. Then there exists a constant depending on H, such that if Q is larger than a constant, then this statement is true without taking this limit as Q approaches infinity. So namely, if you look at the limit for n congruent to 1 mod 2 and n approaches infinity of the expected number of surjections from the class group of OK to H, then this is 1. Okay, are there any questions about that? So, yeah. Maybe one thing I'll say is this doesn't prove the whole Cohen-Lenstra heuristics because of the fact that if you fix a finite field, you're only proving this for finitely many. You're only computing finitely many of the moments of the distribution. But if you fix an H, then actually you're computing the moments for all but finitely many of the finite fields. So if you were able to, if this part of the theorem wasn't there's a constant, if it was just true for all Q, then that would actually prove the whole Cohen-Lenstra conjecture over function fields. And so it's really the fact that it's only for large Q that means that the whole thing isn't proven. But this is really the first computation of any kind of moments of the Cohen-Lenstra distribution, besides the one by Davenport and Heilbronn. Okay, so let me know if there are any more questions, or I'll say a little bit about why this turns out to be a problem in topology. Okay, so how does this work? Like why is this a problem in topology? So the strategy roughly goes like the following. So we're trying to understand the following data. We have some hyperelliptic curve, and we have some map from the class group of that hyperelliptic curve, some surjection to H, and we want to count how many of those things there are. And there's a scheme over FQ whose FQ points that are exactly counting these surjections. And it's what's called a pointed connected Hurwitz scheme. And so this thing that we're trying to count is exactly the same thing as FQ points on some Hurwitz scheme. So this is some scheme. And there's a Grothendieck-Lefschetz trace formula that tells you that if you have a variety over FQ, you can understand its number of FQ points by understanding its étale cohomology and understanding the Frobenius action on the étale cohomology. And so via the Grothendieck-Lefschetz trace formula, and also you need to know something about the eigenvalues, but that we just use Deligne's bounds on the eigenvalues of the Frobenius. You can understand the number of FQ points by trying to understand the étale cohomology of Hurwitz schemes. And if you want to understand, and now there are comparison theorems that say that étale cohomology, so these Hurwitz schemes, they're really defined over the integers after inverting finitely many primes. And so there are comparison maps between, you can base change to the complex numbers and then look at the complex variety that you get. Or you could base change to FP, which is the thing that we're trying to understand. There are comparison theorems between the different cohomologies that you get. And that tell you that actually, if you just want to understand the étale cohomology, you can look at the singular cohomology of Hurwitz spaces. And that determines, that's sort of isomorphic to this. in an appropriate sense. And so then the problem comes down to understanding the singular cohomology of these Hurwitz spaces. And so Ellenberg, Venkatesh, and Westerland, what they did is they showed that if you take the homology of certain Hurwitz spaces associated to certain groups and conjugacy classes, they show that these exhibit homological stability. So there's this parameter n, and as you let n go to infinity, the relevant Hurwitz spaces that show up here, their homology stabilizes. And that's actually the key fact that they use to prove the Cohen-Lenstra heuristics. And so what we do is we compute that stable homology. We compute what it stabilizes to. Okay. So are there any questions about this? Because the next thing I'll do is I'll go on to tell you about what these Hurwitz spaces are, and why, and how to compute their stable homology.
But you said there was a mistake. So the mistake is not in the existence of homological stability, but what the stable thing is?
Yes, exactly. So their second preprint was trying to claim that they knew how to compute the stable homology. And they did actually make some partial progress towards computing the stable homology, which I'll mention later in the talk, but they didn't. There's sort of a serious part that they overlooked, which I'll also explain. Okay, so I want to first explain what these Hurwitz spaces are. So let G be a group and C be a union of conjugacy classes in this group. So this Hurwitz space, there's an N, which is, there's an N, and then there's a G, and then there's a C. And you can describe it as the moduli space of G covers of the disk minus N points, equipped with a trivialization, maybe endpoints in the interior, plus a trivialization of the cover at some boundary point. And then the last condition, so and then there's another condition, which is that the monodromy has to be in C. So what do I mean by this? So a point inside this Hurwitz space, it's given by the following data. So you have a collection of n points, and in the complement of this collection, you have a finite cover of the complement of this configuration, which has an action of G. It's a G cover, and then you have a trivialization at some boundary points. And then if you look at the monodromy around any loop going around these points, that monodromy should be in C, in the conjugacy class C. So that's the space. It also has, so the fact that you can describe it in terms of G covers sort of explains why it has it comes from a variety. It's sort of, you can see that it's very closely related to configurations of points on A1, which is why it's a scheme. But it also has a topological description as the following thing. So you can take the conjugacy class, you can take the n-fold product of it, and that has an action of the braid group, which is given as follows. So if you have X and Y, and you look at how one of these braid twists act on it, then it gets sent to Y and Y conjugated, X conjugated by Y. And so that gives an action of the braid group on sort of words of length n in this conjugacy class. And so you can take the homotopy quotient by this braid group action, and that is actually the homotopy equivalent to this Hurwitz space. So just to set up some notation, so these Hurwitz spaces, you can put them all together as all the n's as n varies, you can put them all together. And I'm just going to drop the n from the notation when I do that. So that's the union over all n greater than or equal to 0 of these Hurwitz spaces. And this actually forms an E1 algebra in spaces. So there's a multiplication given by just concatenating covers, or if you want, concatenating words. And so, yeah, so this is an E1 algebra in spaces. And there's a map from this to the configuration space, which I'll use to denote the union of the configurations of endpoints in the disk, which is also just the classifying space of the braid group on letters. And this is really the free E2 algebra on a point. That's what this is. And in fact, the Hurwitz spaces also have an interpretation as an E2 algebra, but not in the category of spaces. So you can also say that this Hurwitz space is it's the free E2 algebra in this category called G-crossed spaces. So what it is, it's a space equipped with the G action and a map to G with a conjugation action. And then there's sort of, this has a monoidal structure, which is just given by the product. And there's sort of an interesting braiding on this category, which is not the usual braiding. And the Hurwitz space is actually the free E2 algebra on C in this category, which is a braided monoidal category. And so, yeah, so there sort of is a nice homotopy theoretic description of this. And in some sense, this computation can be viewed as sort of, well, it is really just computing the stable homology of the free E2 algebra in this category. It sort of feels like a nice homotopy theoretic statement. Okay, so I want to explain what the answer is for what the stable homology is. So the theorem that we prove about the stable homology is that you can consider the following map, which is you take this Hurwitz space, and then there's a map to this, you can look at I naught of the Hurwitz space, and then you have pi naught of this configuration space, which is just the natural numbers, and then you can sort of take this pullback. And the claim is that this map is an isomorphism on stable homology. So rationally, or really after inverting finitely many primes. So this is an iso on the rational homology for I less than or equal to an plus b, and a is some positive number. So this is sort of saying that it's true in some stable range. And this is assuming that the homology stabilizes.
The target of the map involves conf GC. What does GC do there?
Oh, sorry, I just shouldn't have written that. So just conf. So in other words, what I'm saying here is that the stable homology of Hurwitz spaces the only way in which it's not the stable homology of configuration space is that there are a lot of components. So it's sort of, what that means is that if you look at any fixed component of Hurwitz space and you're going in a very large degrees, then it will look like the stable homology of configuration space on each component, but there might be multiple components. And so we know, for example, we know the stable rational homology of, we know even integrally the stable homology of configuration space. It's sort of the free E2 algebra with the element inverted. So for example, that tells you that the homology of this is it's just Q in degrees 0 and 1, and it vanishes otherwise. So it's sort of rank 1, degrees 0 and 1, and it vanishes otherwise. And that's what the stable homology is. Are there any questions about this? Yeah. Okay, so how do we, well, so maybe before I get into the proof, I just want to go through some examples. Or I really want to just stick to the case where G is the symmetric group on 3 letters, and C is the conjugacy class consisting of order 2 elements. So namely the transpositions, which are 1, 2, 2, 3, and 1, 3. And I'll just I'll give these names. I'll call this x1, x2, and x3. So the proof is really not so different in general, but it'll help maybe for concreteness to just stick to this example. So first, maybe I'll show you an example of the homology stabilizing. So why, for example, does even pi naught of this Hurwitz space stabilize? So I'm now just going to drop the G and C from the notation. I'll just leave that implicit if that's okay. So what is this? So the Hurwitz space was the braid group action. It was the homotopy orbits by the braid group action. And if you just take pi naught, that's just the sort of strict orbits of the braid group action on this product. And so, for example, if you just look at the first Hurwitz space, you just get C, which in this case is just x1, x2, and x3. And for the second Hurwitz space, what you get, you're going to have x1 squared, which is 2 x1s next to each other, x2 squared, x3 squared. But then you also have words like x1, x2, and then x2, x1. And you also have things like x2, x3, and x3, x1, but those are all equal to each other via the braid group action. And similarly here. So here there are actually 5 components. And then starting from n equals 3, actually the h naught stabilizes. So if you look at the nth Hurwitz space for n at least 3, here's what it looks like. You have x1 to the n, x2 to the n, x3 to the n, and then you have three other elements which are determined by the fact they're determined by the map, their boundary monodromy. So in other words, they're determined by the fact that they're not equal to one of these, and they're given by they're given by some sequence like xi naught all the way up to xin, and you can take the product of these elements. You can just take the product of this word. So this is sort of like a formal word inside this letter, and you can take the product which lives inside S3, and that product sort of determines the class under the braid group action. So there's sort of six components stably in this case. Are there any questions? Okay. So what are we trying to show? We're trying to show that if you take the chains on the Hurwitz space, then there's this comparison map to the chains on pi naught of the Hurwitz space. And then you take this pullback over pi naught of configuration space of the configuration space. And we're trying to show that this map, F, is a stable isomorphism. That would be saying that it's an isomorphism on homotopy groups or homology groups in a stable range. So that's what we're trying to show. And another way to say that is the following. So there's a stabilization operator. So the stabilization operator is, in this case, it's given by taking the sum of the squares of all of these elements, which you can view as, so for xi in this conjugacy class, you can take the sum of the squares. And what we're trying to show is that when you invert the stabilization operator, you want to show that this is an isomorphism. because that's saying that it's an isomorphism in the stable range. And so the thing that Ellenberg, Venkatesh, and Westerland were able to show in their preprint is that if you take this stabilization, if you take this map and you invert a slightly different stabilization operator, namely, instead of taking the sum of all of these elements, you take the product. They showed that this map is an isomorphism. And this is the kind of thing where you maybe, yeah, so this is, these are not the same operators, but this is the kind of thing that is more amenable to sort of standard techniques in homological stability, because this operator exists at the level of spaces. So you can multiply by the element in spaces. Like this is the homology of an E1 algebra in spaces. So you can just multiply by an element, and you can do that multiple times to get a product. But notably, this actual stabilization operator, it doesn't exist at the level of spaces, because it's a sum of it's a sum of operators that exist at the level of spaces. And that's sort of one of the things that makes this a subtle question to try to understand, is the fact that, and I think, yeah, so the fact that this is not coming from the level of spaces was sort of a sort of stumbling point on this with respect to this problem. So the main technique to get over this point is to try to decompose this map that we're trying to show as an isomorphism. And the way you want to decompose it is by sort of thinking geometrically about the problem, where you think of these as like functions on some space, and then you sort of think that you can look at the locus where they're zero, and you can look at the locus where they're invertible, and you can sort of decompose the space into those two pieces. So more precisely, let's imagine that you have some map of E1 rings. So this is an example of a map of E1 rings. And let's say you have some element alpha in pi naught of R. Then what you can easily see is that this map is going to be an isomorphism if and only if it's an isomorphism after completion at alpha and inverting at alpha. And saying that the completion is an isomorphism is equivalent really to saying that, well, yeah, maybe I just won't say more. But so you just need to check that sort of, so if anytime you have an element, you can sort of decompose into the locus where you're sort of complete with respect to that element, or where you've inverted that element. And we want to apply this to the situation where alpha is all of these elements, x1, x2, and x3. And we want to take this G to be this map that we're interested in, showing as an isomorphism. So we're going to decompose the map that we're interested in into sort of the locuses where some of these things act invertibly and some of them are topologically nilpotent. Okay. Are there any questions? So, okay, so by sort of applying this, we can apply this fact for all of these elements, and what you end up with is the following statement. So we're trying to show that F adjoin U inverse is an isomorphism, and we learn that that's true if and only if for all subsets of this conjugacy class, if you take F and you invert U, and then you also invert the elements inside the subset, and then you complete at all the elements not in the subset, we need to show that this is an isomorphism for all subsets. And yeah. So we sort of decompose this map into sort of more elementary pieces like this. Okay, so let's think about all the different cases now. So first there's the case where S is actually the empty set. So in that case, what we're looking at is we're looking at F adjoin U inverse, and then we're completing at x1, x2, and x3. And we want to show that this is an isomorphism. But I actually claim that actually both the source and target are 0. And why is that? So, well, what is this operator u? It's sort of the sum of xi squared. And it's a unit. But on the other hand, these xi squareds, they're topologically nilpotent. And that's because we've completed at all of them. And so their sum is also topologically nilpotent. And therefore, U is both a unit and topologically nilpotent. So this thing is just 0. This operation of just inverting U and then completing is just 0. So source and target of the map are both 0. Okay, so that one wasn't so interesting. So then there's the case when S is the whole conjugacy class. So in that case, when you invert this U, and then you're inverting the whole subset. You're inverting every single thing in this conjugacy class. And there, that's just the same as if you invert a bunch of elements, that's the same as inverting their product. So that's in other words the same as inverting the product of these xi squareds. And that was exactly what Ellenberg, Venkatesh, and Westerland showed as an isomorphism. And so this one we're sort of already okay, because that was sort of the part that was already known to be true. Okay, so the other case that you have to think about is, so then the other case is when maybe S has size 2. So in that case, what does it look like? Then it looks like you're maybe inverting 2 of these elements, and then you're completing at the third one. But now I actually claim that, again, the source and target of the maps are 0. So why is that? It's because of the following relation. So I sort of told you before what the pi naught of her2 looks like. In particular, we saw these relations over here, and we have this relation x2 x3 x2 equals x2 x1. And what is this saying? Well, you can multiply by x2 inverse on the right because here x2 is a unit. So that's saying that x3 is actually equal to x2, x1, x2 inverse. And now the right-hand side is a unit. So the left-hand side is also a unit. But on the other hand, it's topologically nilpotent because we've completed with respect to it. So this is a unit and topologically nilpotent. So that means that the source and target are 0 again. Okay, so again, that wasn't so interesting. And I mean, the reason is, I was saving the most interesting case for last, which is the case that the size of S is just 1. So in that case, what are we doing? We're looking at this comparison map, and we're inverting a single element, maybe x1, and then we're completing with respect to x2 and x3. Okay, so, and we need to show that this is an isomorphism. So the first observation to make is that actually this completion process is really well behaved. In fact, at the level of homotopy groups, or homology groups, it's literally just given by quotienting out by the ideal generated by x2 and x3. And the reason for that is we have the following relation, which is that if you take x2 cubed times x1, that's the same as x1 times, x2 cubed times x1 is the same as x2 times x1 cubed. And the reason is because we're sort of in the place where the H0 has already stabilized. And so this is just a relation that's true via the braid group action. You can see that from the fact that the product of these elements in the group, the symmetric group, are the same. Because x2 squared and x1 squared are both the identity element. And so what this tells you is that if you look at x2 cubed, it's equal to x2 x1 squared if x1 is invertible, which is true here. And so what that's telling you, that's kind of a weird situation to be in. It's saying that a larger power of, like, x1 is a unit. So it's saying that a large power of x2 is it's divisible, it divides a smaller power of x2, or it's really the same as a smaller power of x2 up to a unit. And that's kind of a strange situation. And it actually implies that if you look at x2 squared times x1 to the minus 2, this is a central idempotent. Inside this ring. And what that actually tells you is that this completion operation is actually just inverting some idempotents. And that means that it's really well behaved. Most of the time, completion isn't just inverting an idempotent. So yeah, and so from this fact, you can learn that this operation of completing at x2 and x3, it just sort of inverts x1, and then it quotients the ideal generated by x2 and x3. Okay. And so if you think about the definition of the target, so let me go back a few pages. So we were considering this map from the Hurwitz space to this sort of thing that was the configuration space pulled back over the, like, sort of spread out over the components of Hurwitz space. And now we're sort of getting rid of the components of Hurwitz space that had an x2 and x3 in it. That was sort of what this completion operation does. And so it only leaves the components of the Hurwitz space where the x1 was there. And so in other words, after you do this completion, the target of this map just looks like a configuration space, where but it's like a configuration space on the element x1. And so yeah, so you learned that the target of this map that we were interested in, we were studying this map from A to B. And we learned that, after you invert this element and complete at the other two elements, then you just get a chains on configuration space, where sort of you think of it as being the configuration space where it's sort of the words x1 to the n, kind of. And then you invert x1. And actually, at this point, this map F, it actually comes from a map of spaces, but not quite spaces, but pointed spaces. And so, yeah, so the claim is that this map that we're interested in, it's induced by taking the reduced chains of a map of E1 algebras in pointed spaces. And what that map is the following. So you look at, so we're looking at this Hurwitz space for the group S3 and this conjugacy class, and we just add a disjoint base point to it to think of it as a pointed E1 algebra in pointed spaces. And now there's a restriction map that goes to the configuration space. And what it does is it's kind of a silly map. It just takes all of the components that were in this Hurwitz space that weren't of the form x1 to the n, and it just sends those to the base point. And so that's a map of E1 algebras in pointed spaces. So it sends, so this configuration space, it naturally lives as a sub algebra of this E1 algebra. And this is sort of a map in the other direction that sends all other components to 0. And so the map that we're interested in, it's actually obtained by taking the reduced chains of this restriction map and then inverting the element x1, and then maybe also completing, but yeah. But the point is that now both the source and target are like kind of reasonable things. Before we had this pullback of spaces, and now there's just the space showing up. And so now we're going to use the following lemma, which which is the sort of key input in showing that this map is an equivalence, which is sort of saying that if you want to check, you should view it as it's saying that if you want to check a map's an equivalence, you just need to check something on pi naught, and then you need to check some sort of cotangent information being an equivalence. So if you have a map of connective E1 algebras, and let's say that pi naught of G is an isomorphism. And let's also assume the following condition, which is sort of something about the cotangent complex, if you appropriately interpret it. So you want to assume that pi naught of S, if you take the relative tensor product over R of pi naught of S, then that's the same as taking the relative tensor product over S. So if you assume that this map is also an isomorphism, then actually just G is an isomorphism. So we're going to apply that to this map of interest. We're looking at some map of E1 algebras. And sort of by construction, pi naught is an isomorphism because we sort of defined this map F to be such that we sort of spread out the components such that pi naught was the same. And so when you apply this lemma, what you end up having to show is the following thing. So what is pi naught of this S in this case? It's the chains on pi naught of this configuration space where you've inverted this element. And so the pi naught of configuration space is just the natural numbers. It's determined by the number of configurations. And so when you invert that, you get the integers, and then we're adding a base point to everything. And so what we end up having to show is that if you take the integers and you take this relative tensor product, which is a two-sided bar construction in spaces of this Hurwitz space, then that would be the same as if you just did it for the configuration space. So this is just a statement about some two-sided bar constructions in the category of pointed spaces. And you can sort of reduce this map being an equivalence to checking that this map of pointed spaces is an equivalence. And this is really the core thing that you need to get the whole proof to run. And so, okay, so how do we do this? Well, there's really an explicit model for what these two-sided bar constructions look like for Hurwitz spaces. And it has to do with the fact that these Hurwitz spaces, they have universal properties. They're sort of free E2 algebras in some category. And because of that, computing bar constructions over free E2 algebras is a pretty reasonable thing. So I'll tell you an explicit model of this two-sided bar construction for Hurwitz space. So it looks like the following thing. So a point in the space, it's either the base point, or it looks like you have some element m or n, where m and n are integers, because that's the thing that we're taking the tensor product over. So we're looking at this Z plus tensored over Hurwitz space of Z plus. And a point in the space, it looks like you have a sort of configuration of points where these are sort of elements inside the conjugacy class. And you require that they be on different rows. So you want that like each row has at most one point. So you can't have two of these points on sort of the same line, horizontal line. And then so these should sort of be these alpha. You can view these points as being sort of labeled by the conjugacy class C. But then there's a rule that, when 2 points move past each other, then the labels change a little bit. So if you have two labels like this, and then they sort of swap such that they're like that, then this one gets conjugated by that one. So you get like alpha 1, alpha 2. Maybe you get sorry. You get alpha 2 inverse alpha 1, alpha 2. Yeah, so you view these, it sort of looks like these kinds of things where these have some labels, but then there's some rule about if you move these past each other horizontally, then the labels change in some way. And then labels are also allowed to hit the boundary. And if an x1 hits the boundary, it disappears and adds 1 to the boundary. So the boundary is some integer. The boundary has some integer label on it, and it adds 1 on the boundary. And if an x2 or x3 hit the boundary, then you go to the base point. So that's what this space looks like. So you sort of have these points that are allowed to move around, but they're not allowed to cross horizontal lines, and then they're allowed to hit the boundary. And if they hit the boundary, then either you go to the base point or it just changes the boundary label by 1. Okay. And if you look at the analogous thing for configuration space, you see that it's exactly the same space, except that the component of the base point is literally the point. And so what you end up having to show is that the component of the base point of the space is contractible. And there's actually a very simple contracting homotopy, which I can try to explain. So let's say you have a point in your space, and it's given by some things that are labeled by, maybe you have some x2s and some x1s, and some x3s. And you want to define what the null homotopy does to these points. So here's what the null homotopy is going to do. You sort of look at the first point, you start from the bottom and you look at the first point that's not labeled by x1. And such a point exists because of the fact that you're at the component of the base point. Because you assume that the point was at the component of the base point, you have to have some label that's not just x1. And so now what you can do is you can draw a line slightly above that point, and then you have some labels maybe on the boundary n and m, and then what you can do is you can uncollide a point labeled x1 from the boundary. So then this label goes to n-1, and then you get some point labeled x1 on very close to the boundary, and then in your homotopy you're going to sort of move this across this line. And so, when you cross it by this x2, it's going to get conjugated because of this rule. It will get conjugated to an x3. And then when you move it past this x1, it will get conjugated again, but it will get conjugated to an x2, and it won't get conjugated back to an x1. And so when you reach the end of this homotopy, you will have something that's labeled by something that's not an x1. And because of that, when it hits the boundary, you're going to go to the base point because of this rule. The rule is that if one of these things hits the boundary, then you have to hit the base point. And so this gives a contracting null homotopy of the component of the identity, the component of the base point, and that finishes the proof. Yeah, I'll stop there.